So today I'm reading Putting an End to End-to-End, the gradient isolated learning of representations. This one is from Lev, O'Connor, Welling, from AM Lab, University of Amsterdam. So abstract is following. We propose a deep learning method for local self-supervised representation learning that does not require labels nor end-to-end backpropagation, but exploits the natural order in data instead. Inspired by the observation that biological neural networks appear to run without backpropagating a global error signal, we split deep neural network into a stack of gradient isolated modules. Each module is trained to maximally preserve the information of its inputs using InfoNCE, bound from Oord et al. 2018. Despite this greedy training, we demonstrate that each module improves upon the output of its predecessor, and that the representation created by the top module yield highly competitive results on downstream classification tasks in audio and visual domain. The proposal enables optimizing modules asynchronously, allowing large-scale distributed training of very deep neural networks on unlabeled datasets. Okay, so I think I've read a paper which was a little bit similar to this one. They instead used this sort of improved correlation. So instead of correlation, they used a Hilbert-Schmidt norm tests for independence, and then using that they made sure that different layers of the network sort of behave statistically differently statistically uncorrelatedly, and they did that. But here instead of layers, I guess they have these sort of modules, and they use different methods, InfoNCE. So introduction. Modern deep learning models are typically optimized using end-to-end backpropagation and global supervised loss function. Although empirically proven to be highly successful, Krzyzewski et al. 2015, this approach is considered biologically implausible. For one, supervised learning requires large labeled datasets to ensure generalization. In contrast, the children can learn to recognize new category based of few samples. Additionally, despite some evidence for top-down connections in the brain, that does not appear to be a global objective that is optimized by backpropagating error signals. Instead, biological brain is highly modular and learns predominantly on local information. In addition to lacking natural counterpart, the supervised training of neural networks with end-to-end backpropagation suffers from practical disadvantages as well. Supervised learning requires labeled inputs, which are expensive to obtain. As a result, it is not applicable to majority available data and suffers from high risk of everything. At the same time, end-to-end backpropagation is potential memory overhead. Working memory, intermediate outputs, this enables application of deep learning without dimensional able the suppress current memory constraint. This problem is perpetuated as end-to-end training does not allow for exact way of asynchronously optimizing individual layers. Okay. We optimize as well for success to provide gradients. Okay, figure 1. The greedy InfoMax learning approach. Left. For the self-supervised learning of representations, we stack number of modules through which the input is forward propagated in the usual way, but the gradients do not propagate backward. Instead, every module is trained greedily using local loss. Right. Every encoding module maps its inputs at the time step t to GM encoder gradient block, which is used as an input for following module. The InfoNCE objective is used for greedy optimization. This loss is calculated by contrasting the predictions of a module for its future presentations against negative samples, which enforce each module to maximally preserve the information of its inputs. Against negative samples, which enforce each module backside preserves information of its inputs. Okay, so here we go. They use contrasting prediction. Which module to maximize the information with input. We optionally employ additional autoregressive modules, which is not depicted here. Okay, so on the picture, here we see these blocks, which represent modules. They are sort of stacked in a tree, where on the bottom there is a data, and there are lots of these modules, and then going further up, and the tree is getting sort of narrower until you are on the top. So InfoNCE objective is on the right. So okay, positive samples, negative samples, and then they sort of have this contrastive objective. This forward and backward locking of the network is called by backpropagation algorithms. They increase this efficiency of hardware accelerator. Okay. Novel learning approach, greedy InfoMax, that improves upon these problems. Drawing inspiration from biological constraints, we remove end-to-end by dividing the gradient isolated modules that we train using greedy self-supervised loss per module. Given unlabeled high-dimensional non-sequential or spatial data being coded iteratively module. By using a loss that enforces the individual modules to maximally preserve the information of their inputs, we enable the stacked model to collectively create a compact representations that can be used for downstream tasks. For our contributions are as follows. The proposed greedy InfoMax algorithm achieves the strong performance on audio and image classification tasks despite this greedy self-supervised training. This enables asynchronous decoupled training of neural networks, allowing for training arbitrary deep neural networks on larger than memory input data. We show that mutual information maximization is especially suited for layer-by-layer greedy optimization, and argue that this reduces the problem of vanishing gradients. Okay, so here we go, mutual information maximization. I guess this is the InfoMax thing, but there is a better approach than this InfoMax maximization. That's called something like Hilbert-Schmidt information criterion. I think so that it performs better than InfoMax and then mutual information. I guess they haven't looked at that. Maybe they mention it below. Background. In order to create compact representations from data that are useful for downstream training, we assume that the natural data exhibits so-called slow features. It is theorized that such features are highly effective for downstream tasks such as object detection or speech recognition. To illustrate, a patch of few milliseconds of raw speech utterances share information with neighboring patches, such as speaker identity emotion from memes, while it does not necessarily share with these random patches from other utterances. Similarly, a small patch from mature image shares many aspects with neighboring patches, such as depicted object or lighting conditions. We then propose how we can exploit this to learn representation that maximize. Okay, here we go. 2018, they proposed to maximize mutual information shared among the variable. In this work, we focus especially on contrastive predictive coding. This self-supervised end-to-end learning approach extracts useful information from sequential inputs by maximizing mutual information between extracted representations of temporally nearby patches. So once again, this self-supervised end-to-end learning approach extracts useful representations from the sequential inputs by maximizing the mutual information between the extracted representations of temporally nearby patches. In order to achieve this, CPC first processes the sequential input signal X using a deep encoding model, and additionally produces a representation that aggregates the information of all patches up to time step using an autoregressive model. Then mutual information between the extracted representations of temporally nearby patches maximized by employing specifically designed global probabilistic loss, following the principle of noise contrastive estimation. Then mutual information between the extracted representations by patches is maximized by employing specifically designed probabilistic laws. Okay. CPC takes a bag. For each delay, positive sample which is encoding of input flows. Negative samples are uniformly drawn from all available encoding sequences. Each pair of encodings is scored using function to predict how likely is it that the given is a positive sample. In practice, use of log bilinear model with unique weight metrics for each case steps ahead prediction. The scores from F are used to predict which sample in the bag X is correct using the InfoNCE loss. Okay, so in this InfoNCE loss is minus sum over K. Then there's a average or expected value over X. Then we have a logarithm of this f of the fraction of f function on top divided by sum of this fi. So this loss is used to optimize both encoding model and the autoregressive model to extract features that are consistent over neighboring patches, but which diverge between random pairs of patches. At the same time, the scoring model F learns to use those features to correctly classify the matching pair. In practice, the loss is trained using stochastic gradient descent with minimages drawn from large datasets of sequences and negative samples drawn uniformly from all sequences in minimatch. Note that no minimax issues arise as found in adversarial training. As a result of this configuration, one can derive that the optimal solution for F is proportional to the following density ratio. Probability ZT is the condition on CT divided by probability. Okay, I'm not gonna read the maths here. This insight allows us to reformulate minus L loss as a lower bound on mutual information, as demonstrated in the appendix of and provable. Okay, so minimizing the loss thus optimizes the mutual information between the consecutive patches representations, which in itself lowers the bounds the mutual information, lowers bounds the mutual information between the future input and the current representation. In 2016 paper shows that the similar patch contrastive setup leads to extraction of set of conditional independent components such as Gabor-like filters found in early biological visual system. Leira's information preservation in neuroscience. Linksker 1988 developed the InfoMax principle in 1988. It theorizes that the brain learns perceptions by maximally processing the information of the input activities in each layer. On top of this, neuroscience suggests that the brain predicts future inputs and learns by minimizing the prediction error. Empirical evidence indicates, for example, that the retinal cells carry significant mutual information between current and future state of their activity. Greedy InfoMax. In this paper, we pose the question if we can effectively optimize the mutual information between representation and each layer of the model in isolation, ensuring the many practical benefits that greedy training provides. In doing so, we introduce a novel approach for self-supervised representation learning. Greedy InfoMax. As depicted on the left side of figure 1, we take a conventional step deep learning architecture divided by depth into a stack of M modules. This decoupling can can happen at the individual level, or for example, an individual layer level, or for example, at the level of blocks found in residual networks. Rather than training this model end-to-end, we prevent gradients from flowing between the modules and employ local self-supervised loss instead of additionally reducing the issue of vanishing gradients. As shown on the right side of figure 1, each encoding module within our architecture maps to the output of previous module. Encoding, no gradients are flowing between the modules. Opposed to its output autoregressive models to contrast against the future variations. However, our preliminary results showed that this did not improve results if applied at every module in the stack, and optimizing it requires backpropagation through time, which is considered biologically impossible. Therefore, we train each module using module local InfoNCE loss. After convergence of all modules, the significant scoring function can be discarded, leaving conventional feed-forward neural network architecture that extract features from downstream tasks. For certain downstream types, several contexts is essential. For example, in speech recognition, the receptive field might not carry enough information to distinguish phonemic structures. To provide this context, we reintroduce autoregressive model and as an independent module that we can optionally append to the stack of the encoding modules, resulting in the context aggregate representation. In practice, GRU or Pixel CNN style model can serve this role. We train this module independently using following altered scoring function: iterative mutual information maximization. The results outperform end-to-end. Wait a minute. As shown in table 1, greedy InfoMax outperforms its end-to-end trained CPC counterpart, despite its unsupervised features being optimized greedily without any backpropagation between modules. An equivalent randomly initialized feature extraction model exhibits poor performance, showing GMI extracts useful features. Training the feature extraction model end-to-end and fully supervised performs worse, likely due to the small size of the annotated dataset resulting in overfitting, although this could potentially be circumvented through regularization techniques. The self-supervised methods do not appear to require regularization as they benefit from the full unlabeled dataset. Using a greedy supervised approach for training the feature model impedes performance, which suggests that mutual information maximization is unique in its direct applicability to greedy optimization. This deep InfoMax model, predecessor model. Alright, I'm gonna quickly skim through this part. Related work. Conclusion. We presented greedy InfoMax, a novel self-supervised greedy learning approach. The relatively strong performance demonstrates that deep neural networks do not necessarily require end-to-end backpropagation of supervised loss on perceptual tasks. Our proposal enables greedy self-supervised training, which makes the model less vulnerable to overfitting, reducing the vanishing gradient problem, and enables memory-efficient asynchronous distributed training. While the biological possibility of our proposal is limited by the use of negative samples, and within the module backpropagation, the results provide evidence that theorized self-organization in biological perceptual networks at least is feasible and effective in artificial networks, providing food for thought on credit assignment discussion in perceptual networks. Okay, so once more. Greedy self-supervised training, less vulnerable to overfitting, vanishing gradient problem, and memory efficiency. Alright, thank you very much. If you have any suggestions, let me know, and hopefully see you next time.